Now to answer this, think about the following. Say there are some landmarks and we observe them from a certain position. Then essentially what we do is that we set up a link between the positions of our landmarks where we do not directly observe the distance between two landmarks, but rather we observe them through an intermediate point, which happens to be the position of the robot at that point in time. Now if you move for a while, by all those measurements, the distances between our landmarks become very accurately known. And so the random error of those relations between the landmarks becomes smaller and smaller. So you can think of this as some kind of elastic bands that allow those points to move freely, and then with every measurement, those bands become less elastic and the distances become fixed. Now does this mean that the error ellipses of all the landmark points go to zero, or at least become very small? And this is actually a problem of the anchor, or in geodesy it's also called the datum definition, which means that even though I know all those distances very accurately, I don't know the position of this entire structure in space. So as we have set up the problem, everything is tied to my coordinate system, which happens to be at the center of my robot's initial position. And if the error at this initial position is assumed to be large, then this entire structure can move by that amount, as it is tied to this initial position. So if you set the error to be large in the initial position, then the errors of all the landmark positions will never become zero or close to zero, no matter how many measurements you take. Now let's have a look at the dynamic Bayes network, which describes the state transitions of our robot. So the x is our state, and here we have the transition, which is controlled by our control input u, and in each state we do a measurement, and the value of this measurement depends on the current position of the robot and on our map. And so what I just described is also termed the online SLAM problem, namely we want to know the probability for our current state and for our map given all our measurements and all our control inputs. When I explained this, I explained it for the case of modeling this probability using a multivariate Gaussian distribution. And so this means in the dynamic Bayes network, I'm interested in this state and in the current map. Now the problem with this is that all the information here is subsumed into this last state. And so if you don't do this, the problem is called the full SLAM problem, in which I determine the probability for all states, that is over all time steps and the map, given all my measurements and all my controls. And in this case, I determine the map and all the states. And this is more desirable, although usually it is infeasible. Now, how can I compute those probabilities? Now, there's two principal problems which make the SLAM algorithm computationally expensive. There is a continuous component, which we already outlined. We have to compute the x, y, and theta of the robot, but also the x1, y1 position of the first landmark, x2, y2 of the second, and so on, until the nth landmark. And this is just for the online SLAM algorithm. And so as you see, the number of those continuous variables may become very large. And there is a second problem, which is the discrete component of the SLAM algorithm, and which involves the following. My robot observes some landmarks, and then it moves a bit. Well, this movement is noisy. Then again it observes some landmarks. So now, how do we know the correspondences? Now this might be this landmark, and this might be that landmark, whereas this is new. But it might be also the case that this landmark actually belongs to here, and this to here, and the shifts that we seemingly see here were just introduced by a large error in the movement of the robot. And this is actually a very tough problem, because in every step of our state transitions, we have to introduce those measurement values in order to correct our state. So if you remember, we had our predicted belief and our corrected belief. But in our case, this correction involves assignments of landmarks. And so if we do the wrong assignment, we may either shift the robot's position into the wrong direction because of that wrong assignment, or on the other hand, we might miss a correct assignment and introduce a new landmark, although it is a landmark that we already observed. And this means we would not correct the robot's position even though we should. And so these assignments, which are discrete in nature, might introduce errors which might lead much later on to large errors of our state, which we then can't correct anymore because we don't keep track of those assignments. So the assignments we make here lead to a posterior x, and then all this information is lost. And this posterior x, or this posterior belief, is the only information that is kept. So this is the discrete component, which is the correspondence of objects to previously detected objects. And so in general, calculating the full posterior is usually infeasible due to those two problems. So because of the high dimensionality of our parameter space and because of the large number of correspondences in our correspondence assignment. Now, before we go on, let me ask you a question. Say we drove with our robot for a while, say from T1 to T200, and while we drove, we observed 50 landmarks, M1 to M50. So the question is, for the online SLAM problem, how many variables would be in our state?